afternoon to all participants and guest speakers, Professor Dr. Susmita Surkole from ISI Kolkata. So again, I'm welcoming you all to this second day of the event of this short-term training program, Quantum Computing and its Applications. So before hand over the session to Professor Kole, I want to give a brief introduction about Professor Kole. So, Professor Susmita Surkole received the BTech degree in Electronics and Electrical Communication Engineering from IIT Kharagpur and PhD degree in Computer Science and Engineering from Jadavpur University. She has been a faculty member in Advanced Computing and Microelectronics Unit of the Indian Statistical Institute, Kolkata since 1999 and is presently a professor. During the period 1993 to 1999, she was a reader in the Department of Computer Science and Engineering of Jadavpur University. Prior to that, she was a postdoctoral fellow at the University of Nebraska-Lincoln and a research assistant at Laboratory for Computer Science in Massachusetts Institute of Technology. She was also a sabbatical at Princeton University and Intel Corporation, USA. Her research contributions are in the areas of electronic design automation for VLSI physical design, fault modeling and testing, synthesis of quantum computers, and graph algorithms. She has co-authored several technical papers in leading international journals and referred conference proceedings and a chapter in Handbook of Algorithms for VLSI Physical Design Automations. She was the technical program co-chair of the 18th International Conference on VLSI Design and 11th Synopsian on VLSI Design Test in 2007. She has served on the editorial board of IIT Computers and Digital Techniques, IEEE Transaction on VLSI Systems. She is a distinguished visitor of IEEE Computer Society of India, senior member of IEEE, member of ACM, IET VLSI Society of India. Among other awards, she was the recipient of the President of India Gold Medal at IIT Kharagpur and IBM Faculty Award in 2009. So we are very happy and glad to have Professor Dr. Susmita Surkole with us. So now I would like to hand over the session to Professor Kole. Ma'am, please.
Thank you, Dr. Das. Thank you for your kind invitation to this week-long program on hands-on training for on quantum computing and its applications. So good afternoon to everybody. Thank you for the kind introduction. Yesterday, I believe that you have had a nice introduction to the principles of quantum computing, and also a little bit of what happens in quantum, if you want to use quantum computer, maybe the IBM one. So today my plan is, in an hour, I would like to give you a glimpse of the quantum algorithms themselves, and something which has come up, a very interesting group of quantum algorithms, which are called the quantum approximate optimization algorithms. I believe most of you are from quantum computer science and information technology background, so it's sort of aligned to that part. Yeah. So the brief introduction that I have in my talk, I guess I can just rush through them because you already know of that, and then start mainly from the second part, which is the quantum algorithms. And the three famous quantum algorithms, which has made everybody sit up and start looking at building quantum computers, namely the Deutsch-Church's problem, Shor's factoring algorithm, and Grover's search algorithm. Uh, in a span of 1 hour, it's not possible to cover the details, but I'll try to give you the key idea of how the quantum system helps in speeding up these algorithms. And then we move on to the realistic quantum computing scenario, which is in the presence of noise and the effect of it, and so on. So although I wanted to talk about quantum error correction, I'm not sure whether we will have enough time, perhaps at some other time. So what are the major drivers of quantum computing? First of all, there are algorithmic limitations in the sense that quantum mechanical laws can speed up computational processes by massive parallelism over classical models. Yesterday, you may have heard about superposition and quantum entanglement. So the superposition is what is referred to as massive parallelism, and I'll elaborate on that in some of the algorithms that we'll talk about. And at the other end, the hardware limitations, because the computers are getting smaller and faster, no doubt. All of us have at least one computing device in our pockets, namely our mobile. The smartphones can do a lot of computing. You have these integrated circuits in every direction that you look at. However, the scale of integration is reaching a point where classical physics is no longer a sufficient model for the laws of physics. The chips with 14 nanometer feature sizes are available. We are heading towards 10, 7, and maybe 5 nanometers. And you can just imagine, if you think about the size of an atom, how small things are getting. And if it gets to that level, then the classical digital electronics of Boolean algebra, those things seem to break down. Just as Einstein's general theory of relativity is applicable when things get close to speed of light as opposed to Newtonian mechanics. So historically, the idea of computing first came along with Alan Turing in 1936 when he proposed the Turing machine as a model for, it's an abstract model for computation. Almost 50 years later, Richard Feynman, the Nobel laureate physicist, he had this brilliant idea that, there's a limit to the model of computing that Turing's model has. And to overcome that, to solve problems which need large amount of computation, we may make use of the quantum systems to, in fact, solve such problems. So this was in 1982. It's amazing that I was at the talk when he was present. I was a graduate student at MIT then, but it did not register much. It was more of a physics problem. And about 30 years later, I really started looking at the prospects. But in the meantime, what happened is very soon, another theoretical physicist, David Deutsch, actually showed that you can get speed up. And we'll talk about how. And 12 years later, it was only when Peter Shor, another mathematician, showed that you can factorize an integer in polynomial time as opposed to exponential, using quantum computer as opposed to exponential time in classical model. That's when everybody sat up, because you see, the mainstay of public key cryptography was based on the fact, the RSA, reverse Shami-Radelman algorithm, is based on the fact that it's very easy to multiply two very large prime numbers, but factorization is difficult. So to obtain the key back is difficult, so therefore your system is secure. to obtain the key, you would have to spend a lot of time. But Peter Shor showed that if you had a quantum computer, you would be able to do that fast. So then people started thinking that let's split them and let's try to think about cryptographic systems which can beat or which can do without factorization. So in 2012, so there were physicists, theoretical physicists, there were mathematicians, theoretical physicists coming up with ideas, and mathematicians together with them, they were coming up with quantum algorithms. Experimental physicists were building quantum computers, and in fact that was acknowledged by the Nobel Prize in Physics in 2012 to these two very renowned physicists who were able to experimentally prove that you could measure and manipulate individual quantum systems which are needed for doing quantum. Here is some old pictures of quantum computers based on nuclear magnetic resonance here. These are quantum dots, more of solid state. And the superconducting processor is what is more common now with the IBM machines. So this you already know that, you have in a quantum system, the notion of qubit, you can think of two basis states, and you can apply an operation which is a field, and you get to another state. Okay, so this actually gives you the premise for superposition, because if you have four individual independent closed quantum systems, each representing one of these what are known as qubits, if you perform this Hadamard operation, this is causing equal superposition of the two possible states. Okay, so if you do it for 4, then you would get 2 to the 4 possible states. So which means what you have here is a combination of all possible states that could have happened over here at one go. Okay, so therefore, if you measure, then all the possible states have almost equal probability. Okay. There are other operations like the rotation operations. So quantum is more analog rather than digital. Depending on the angle at which you rotate, the state differs. As you can see, the vector here gets rotated by pi by 3, and so therefore this is what you will get. Okay, you can have 2 qubit operations, the C0 operation, which you have already seen yesterday, I'm sure. And the idea is that one of them is called the control. So depending on whether it's in the 0 state, if it is a 0 state, nothing happens, no change. If it is in the 1 state, it can control and swap. That means the NOT operation happens. Okay? So this is an important operation which is used in many of the algorithms. So a quantum circuit is actually a sequence of mathematically represented by matrices. So what does the matrix stand for here? Here are the all possible inputs. So if you have a single qubit, there are 2 possible inputs. And here are the all possible outputs. So there are 2 outputs. And a 0 here means that, a 1 here means that, because it's a NOT gate, if you give an input 0, you'll get an output 1. So corresponding to that, you'll have the 1. So this is actually what is the function of the operation, the output that is represented. I will not get into much details, but these are sort of, so just briefly, if you have control NOT, you see, so this is 0, 0, 0, 1, 1, 0, 1, 1. The first one represents the control. So the first 2 rows are for when the control signal is 0. So nothing happens. So it's the diagonal, whatever is the input, means the output. But when you have 1 in the first qubit, the second qubit is changed. Okay, so it toggles. So that's how the C0 operates. So quantum circuit here is a sequence of such operations performed on a qubit or maybe 2 qubits and so on. So, and unlike electronic circuits where you have these lines as wires and these gates as, you can have NOT gate, you can have NAND gate, 2 input gate, 3 input gate, or 1 input gate, so on and so forth. So that you have a physical location on the chip. So there are some transistors out there. And the change of state of these gates happen by flow of current or through, charge carriers. in the semiconductor. But in quantum, it's completely different. So depending in electronic systems, depending on the number of operations, your circuit size increases. In quantum circuits, it's only the qubits that are physically there. So the lines here actually are timelines. So this means that the first Hadamard operation on qubit 0 and a separate Hadamard operation on qubit 1. Next cycle, you have a C0 operation involving both, then only another rotation gate operation only on the second qubit. So these are actually along the time, these are some measurements. So it's actually a sequential action of quantum gates, okay? And the qubit is not displaced in time. It only evolves over time, it changes, okay? After computation, the qubit is measured and you actually check at in which state it is, and by that you will be able to figure out what the so if it is completely superposed, ideally in the closed system it's in equal probability in both the systems, but the moment you measure by Heisenberg's uncertainty principle, it collapses to one of the two with equal probability, but you will see exactly one of them. Now, the idea of quantum algorithm is such that you start with some input state, easy to prepare input state, and then after a sequence of operations, you want to increase the probability of the qubit or the state which corresponds to the correct output for your problem. So therefore, the design of the quantum algorithm is again like in all algorithms, the intermediate operations that you do so that finally you get to a state which corresponds to the correct output. So as I said very briefly that, these led to a lot of promise for quantum computing. And actually the main promise comes in simulating large systems, microscopic systems, atomic systems, quantum mechanical systems. There's a site in which you can check up. It's called the Quantum Algorithm Zoo, and that gives you the series of quantum algorithms which have been discovered so far. And the main categories are algebraic and number theoretic, where you get very large speed up over classical. Then there are some kinds of search type of problems which are which start from the Grover search algorithm, and then the approximation algorithms. So let's just look at the first three problems since it's a supersonic view. So what is the problem? So initially, Deutsch, it was Deutsch's problem, and then his student, with Joshua, he made it more general. So the idea is as such: you have a function which has an input as a string of length n bits, having n bits. So it's a n bit vector, and the output is 1 bit. Okay, so now the question is, if you are, so remember, if you have n possible variables, you can have 2 to the n combinations of inputs, and therefore the number of functions that distinct functions that you can have is 2 to the power 2 to the n. It's a large number of functions. Now the question is that if you are told that the function, you don't know what the function is, it's a black box, but all you know, it's the promise that you are given is that it's either a constant function. So the figure here, if my mouse is visible, then the figure here is showing a constant function, which means for all values of the input vectors, the value of the function is the same. In this case, it's 1, all 1. It's a constant function. Or it could be a balanced function, which means that among 2 to the n of the possible inputs, for half of them, the function has value 1. For the other half, the function has value 0. Doesn't matter which half. So you can have you can have only 2 constant functions, but you can have quite a number of balanced functions. In fact, you can have these many balanced functions. You can check it. But you don't know which one. So given the black box, how do you determine whether the function is constant or balanced? Okay, what you can do is classically you will have to go through all the 2 to the n values, look evaluations of the function and check whether the values are all same. If so, then you say it's a constant function. If you check that half of them are ones and half of them are zeros, then you say it's a balanced function. Actually, you don't need to go through all 2 to the n. What you can do, because you're told it's either constant or balanced and nothing else, you can actually evaluate half of the input plus 1. So you will evaluate half of them, and then if all of them were same, and the next one, if it is still the same, then you know it's constant. Because if you have 2 to the n minus 1 plus 1 having the same value, then it's definitely not a balanced function. It's a constant function. You're told that it's either constant or not. So this is, so in any case, you would have to do at least 2 to the n minus 1 plus 1 evaluations classical. However, in quantum, you can do it in one step. So the idea is as follows. If it is a n bit string, you need n plus 1 qubits, and this is the cartoon of it, that for the n qubits you do some operation, for the last y qubit you do something else. You design this black box here depending on the black box function in such a way that after your operations, the first n qubits in the output are same as the n qubits in the input, but the last bit is the XOR of this qubit with the value of the function on this. So you can see if the, so we would like to do this in parallel. So how do we do this in parallel? So the first trick is to convert the amplitude to phase, okay, by using this box here, this operator here, U sub f. And the other trick is that you superpose all n qubits with the Hadamard. So first you do this together. So first you do this, all n qubits, all the first n qubits, and therefore you would get all the 2 to the n states here and 2 states over here, because so this is how you initialize the inputs, all to 0. If you have all zeros and apply Hadamard, then you will have all the 2 to the n states with equal probability of 1 by square root of 2 to the n. And the last qubit, the n plus 1th qubit, you set it as 1. And if you apply Hadamard, then the output will be an equal probability, but with a phase. So after you apply this U sub f, you have actually transformed this phase in such a way that if the function is constant, then after measurement of these qubits, you do the Hadamard and you measure it, it is always 0. But if it is a balanced function, then some of them are 0, some of them are, half of them are 0, half of them are 1. So then the R is never 0. So just by doing 3 operations and checking the states, if the states here are all 0, then you say it's constant. If they are not 0, it could be anything other than 0. Okay, you don't care. As long as it is not 0, then you know it's a balance. So with one sort of constant, looking at the measurement only once, that's the query, you can answer the question, which you would have done with 2 to the n minus 1 plus 1 operations. Okay? So classical query, that's the complexity. If you use randomly do it, then you can just randomly choose two different values of the function. If they are equal, you just guess constant. If they are not, then guess balance. But the probability of failure is not zero. Okay? You have a bounded probability of failure. So bounded error query complexity, you have, I mean, the query complexity is how many times you are asking the value. So it's a constant number of times, but there is an error. In quantum domain, you get the exact answer with one query. Okay? So that is the advantage that the first quantum algorithm gave us and made us excited. Now let's move on to the second one and the very important, Shor's algorithm. So if you stare at this upper box, it's actually one big, very big integer written, the digits are written in 5 rows. And if you look at the red ones, it actually writes RSA. And this huge prime, this huge integer is the product of these two huge prime numbers. These two are primes. The first one, both of them are, you know, occupying 4 rows. It's just one number written like this. Okay. If you use the best classical algorithm to factorize to get this answer, you would need order of x e to the power n to the power 1/3 time, where n is the number of digits in the integer that you're factoring. But show that you can do this in polynomial time, which is n cube times log. The idea makes use of an important result from number theory, which was around for many years. It was Fermat's theory, which said that if you choose a number x, okay, and a number n, which are relatively prime, that they don't have a common factor other than 1, then if you take the powers of x modulo n, then it's a periodic function. So let's take x to the 7 and n to the 15. 7 to the power 0 modulo 15. So 7 to the power 0 is 1. 1 modulo 15 is 1. 7 to the power 1 modulo 15 is 7. 7 square is 49. 49 modulo 15. So that means you divide by 15. So 45 and you have a remainder 4. So 7 square modulo 15 is 4. And so on. But notice, the moment you get to 7 to the power 4 modulo 15, it's back to 1 again. So therefore, it's going to repeat 1, 7, 4, 13, 1, 7, 4, 13 till infinity. So, but how does that help us with factoring? Okay, this is the key idea. So I take a slightly bigger number. Let's say that n is equal to 21 and x is equal to 2. Okay, and you find that 2 to the power 6, which is 64 modulo 21 is 1. So the periodicity, which we call R, is 6. Okay, the first value of A for which, other than 0, the smallest value, non-zero positive value of A, for which x to the power A modulo n is again 1, gives the periodicity. So in this case, this value is 4. So in this case, this value is 6. Okay. And it turns out that you can show easily that this is going to be an even number. Okay. So what is R? R is such an integer so that x to the power R modulo n is equal to 1. Now I defined x to the power R by 2. R was even, so R by 2 modulo n to be y. Okay. So in this case, R was 6. So 2 to the power R by 2 is 2 to the power 3, which is 8. Modulo 21 is 8. Now notice, 8 minus 1 is 7 and 8 plus 1 is 9. If you take the GCD of 7 and 21, you get 7. And 9 of 21, you get 3. And lo and behold, 7 and 3 are the factors of 21. Why is it so? Okay, this is because we said x to the power r modulo n is equal to 1. So that means because y is defined in this manner, y square modulo n is equal to 1, which means y square minus 1 is divisible by n. Now what is y square minus 1? It is y plus 1 times y minus 1 modulo n. If that is divisible by n, then the fact, and we know that if n has factors, then these factors should have something in common with either y plus 1 or y minus 1. And therefore, and of course, the values of y plus 1 and y minus 1 are going to lie between 0 and n minus 1. So if you take the GCD of these two, you will get the non-trivial factors of n. Hey, this is very simple. Why didn't we do this all so long? I mean, this looks class 5 algebra. The catch is finding r. Okay. How can you quickly find the value of r for which the periodicity corresponding to x given n? Okay. That is what was taking exponential time, and sure, using quantum computing, made that polynomial. How did he do that? Okay. So what he did was as follows. So you choose an integer which lies in the range of n squared and 2n squared. Okay, initially just check whether n is prime. You can do that in polynomial time, thanks to our own Indian computer scientists, Agarwal, the famous Agarwal, Kayal, and Saxena's AKS algorithm, which was for the first time showed that you can, in polynomial time, find out whether a given number is prime or not. You can check whether it's an even number. You can just divide by 2, or you can also check whether it's a power of a prime. So we can check these quickly. If n is none of these, that is not a prime, not an even number, not a power of a prime, then we know it's a compound number. It will have factors, and we will apply Shor's algorithm. Okay. So the first step is to choose an integer. So you're trying to factor an odd integer n. For simplicity, let's choose 15 again. So 15 square is 225, and this is 450. Let's pick a nice number, 256, which is a power of 2. And we choose a random integer. Again, we pick 7, so that it's relatively prime to n. Okay. Now comes the quantum part. We create 2 quantum registers. Okay. The input register will be large enough to contain enough qubits to represent numbers as large as q minus 1. So we will need 8 qubits. And the output register must have enough qubits to represent numbers as large as n minus 1, which is 14. So we need 4 qubits. So a total of 12 qubits. In one register has 8 qubits, the other register has 4 qubits. So these registers, so if you collapse, I mean, they are entangled in the sense that if you collapse the input register, then it will also be reflected in the output register as well. Okay, so first I load the input register by applying Hadamard equally weighted superposition from 0 to 255. There were 8 qubits, so you have 2 to the 8 possibilities. So all of them are there. Okay, and this is how you show this. So, and A is going from 0 to 255. Okay. So these are the 2 registers. This part is the input register, and this part is the output register. This should have been 4 qubits, showing 3. Anyway, yeah. Now you apply x to the power a on the input register. Okay. So the output register, so you're going to do this, all of them are present, so you can do that in parallel. So the output register is going to have these values, okay? 1, 7, and so there'll be some repetitions and so on. I mean, the periodicity is going to change. If you take a measurement of the output register, then it will collapse to represent just one of the results of the transformation. So remember, the output register will have only, not all 256 values, only some of the values depending, I mean actually as many as the periodicity, whatever the periodicity is. Okay, so it will have exactly 4 values, 4 different values, distinct values. But if you measure, so out of 256 states now you've gone down to 4 possible states. If you measure, it's going to collapse to one of these 4 possible states with equal probability. So let's say it collapses to 1, okay, just for the sake of simplicity. Now things are getting interesting. So the 2 registers are in tandem. We measure the output register, and this will actually have an effect of partially collapsing the input register into equal superposition of each state between 0 to q minus 1 that gave the value of the, so among the 256, only those states which gave the value 1, those are going to be now entangled. So 0, 4, 8, 12, right? 0, 4, 8, they all gave 1. So those are those states are, these will, so the among the 256, instead of that, it will collapse to 64 values. So 256 divided by 4, it's periodic. So groups of 64 will get the same x to the power a modulo n. Okay, so now it collapses to 64 values. Next one. Next, you apply, this is the main quantum step, you apply something called the quantum Fourier transform. What it does, it essentially peaks the probability amplitudes at integer multiples of q by r, where r is the desired period. So in our case, r is 4, we had 64, so q was 256, 256 by r is 64. So you want, the peaks to happen at 0, 64, 128, 192. But we no longer have equal superposition. So the probability of amplitudes of these states are going to be much higher than the other states. And if you measure next, you will be collapsing to one of the states. And that state is going to be a multiple of q by r. Okay? So once you know the multiple of q by r, then by classical methods, you can you know q, you know m. So from those two, you can figure out r. Okay, so that's the idea. Okay? And we figured out that r was 4, and then we can compute the GCD, which can also be done in classical. If Shor's algorithm fails to produce factors of n, for some reason, the measurement was not correct or whatever, all you do is you pick a new x and repeat. So I'll just skip through this. So just to show you, for 21, the q here I've written t was 9, okay, and so 2 to the 9 values over here, x is 2, and so after you applied that, the periodicity for 21 and 2 was 6, so it collapses to fewer states, and then you apply QDFT, so again even fewer states. Okay, and finally, if you do the inverse of it, you will find only 6 states. Okay, and these are actually to the power 9 by 6 times r. So to determine r, you can use conjugate function. So to summarize Shor's algorithm, classical machine takes 2 to the n time steps, quantum machine takes n cube. Classically, if it was a 300 digit prime composite number, it would have taken 10 to the power 6 years. And if it was 1000 digits, it would take 10 to the power 25 years. But in quantum, it can be solved in several hours. The last one is the famous, so Deutsch-Churcha gave you exponential speed up over classical. Shor's factoring gave you exponential speed up over classical. The third one, but it's a very useful one, is for unsorted search. Remember, if you have a sorted list, you can apply binary search and find a given element, if it is there or not, in log of n time, where n is the number of elements. But if it is unsorted, then you have to go through the entire list, so it will be order of n. Using quantum computing, you can reduce order of n to order of square root of n. The idea is as follows. So you start with equal probability. Hello? You start all possible states with equal probability. And let's say, somehow and you are looking for a particular state, whether it's there or not. Okay. So depending on that state, what you do is you apply an operation such that the state corresponding to that value gets a phase inversion. Okay, so after the rotate phase operation 180 degree, this is what happens. And then what you do is you take the average and average of all the values and subtract that average from the values here, and so that's called the diffusion operation. And after this operation, this is the matrix representations of input-output conversion. You find that the marked state, the probability goes up much higher, and for the other states, the probability goes down. And if you keep iterating, this will go closer to 1, and these will be closer to 0. Now the question is, how many times do I iterate? So Love-Grover showed that if the number of entries is capital N, then you take an n-qubit register, small n-qubit, where small n is such that 2 to the n is greater than or equal to n, and you basically can show that you need only a constant times square root of n iterations to be able to answer whether the given item is in the sorted list, in the unsorted list or not. Okay? So that gives you a quadratic speed up. So these are all, there are many quantum algorithms. So these are the key quantum algorithms which we have. So I talked about mathematical, matrix, linear algebraic operations. How do we have physical quantum operations? So to build quantum computers, we need theoretical physicists, experimental physicists, theoretical computer scientists, as well as people like us who are computer engineers, who actually would make use of methods, algorithms to minimize the number of steps. And why is so in order to build a quantum computer, you have to keep two things in mind. That is also there for any electronic circuit, that the number of gates that you use, you want to minimize, and the number of steps or number of gate operations required from the input to the output is as little as possible to build, because that will give you the time required. Okay, you don't want too much delay, and you don't want too many gate operations. In quantum, it's even more important. The reason being that quantum systems are very noisy. There can be gate errors. So which means that, we all along so far, we assumed that the qubit is an isolated quantum system, which could be a photon or a spin ion, trapped ion, uh, okay, or a superconductor, okay. Uh, so and as long as it does not have any interaction with the environment, it in whatever state it is going to be remain in that state unless you apply another operation. And applying an operation means you apply some electromagnetic field to change this state of the quantum system. Okay, but there's nothing called ideal vacuum. There's nothing called ideal isolation. So what happens is there is some interaction, and over time the state decays, and therefore the state changes, okay, which is called noise. So that could be the gate error. Now gate error means that the field that you are applying, that could have some um, noise, some effect which is not ideal. So imagine a C0 gate over here. So in electronics, the gate error, if it is a NOT gate, if there is a faulty gate, then the input was 0, the output was supposed to be 1, but it remains 0. So that's the kind of error that you get. But here what happens is, so for example, C0 gate, so it is restricted to the input output of the single line that is affecting over there. But here, suppose the control line of a C0 gate is noisy, then the output is also noise, has an error. But because of that, the input also, the target qubit also, the effect on the target. So if this was supposed to be 1, and this was 1, this was supposed to be 0. But now instead of 1, this becomes 0. So the first qubit, qj qubit, excuse me, will be 0, that is noisy. And because it's 0, the target qubit will not change. So it will again be 1. So that also becomes erroneous. Earlier, this was supposed to be 0 and no effect on QL, but this remains 1. So again, this is going to change. So in some way in quantum, the error effect is very serious because it propagates because of all that entanglement and all that, it propagates very quickly. There could be also relaxation error because of the idle. If it is idle, then there is interaction, and therefore there is decoherence, and state keeps changing, and therefore so these are the two main kinds of error which affects the computation. Okay, and so the devices we have till now, these have noisy qubits. Okay. Some do not have any error correction. Some may have error correction, but sometimes error correction is not enough. Okay, so we need to come up with algorithms which require small number of qubits and which does not require too many operations in the sequence, and also to be able to uh, uh, deal with an output which may not be the exact output, but an approximate output. In many cases, an approximation solution is good enough. Okay, so some IBM quantum hardware details shows you that you can ignore most of it. We are running out of time. All I wanted to show is that the single qubit gates have much less error than the 2 qubit errors gates, such as C0 gates. It's almost 100 times more noisy. Okay? So when you are designing algorithms for noisy systems available, what we want to do is avoid or minimize the number of 2 qubit gates. So in order to do that, the idea of quantum approximate optimization algorithms came along. Actually the idea of hybrid quantum classical algorithms came. So you have one part which is quantum, another part which is classical, and you can iterate in some sense that you do some parameter optimization here, feed this parameters to the quantum part, and use that to operate the quantum circuit, which is known as the ansatz, measure depending on the output you again iterate. So we want to minimize the depth of these circuits and also minimize the number of parameters over here. Okay. These have lots and lots of applications. Computer scientists are very much interested in combinatorial optimization. There are also recent applications in quantum machine learning, which I won't go into. So QAWA, as it is known, quantum approximate optimization algorithm, is one such hybrid quantum classical algorithm for finding good approximate solutions to um, combinatorial optimization. I will take the example of max-cut, but let me just quickly tell you uh, the, um, the idea of QAWA. So there was this idea of quantum adiabatic algorithm, which means that for any problem, this is more analog, not digital. So you take a problem, you always describe it in terms of a Hamiltonian, and the state, and over time, as the state changes through this Hamiltonian, um, this time evolution, and finally it tends to get to the state with the minimum energy, which is the equilibrium state, and that turns out to be the solution of the Hamiltonian problem. That is how we encode any problem to be solved by quantum systems. But it's difficult to sometimes prepare the ground state of the problem Hamilton. Instead, just as we showed for Deutsch-Dasha, for all the three algorithms, the Shor's algorithm, Grover's algorithm, we saw that we chose a very simple ground state basic Hamiltonian, which was all zeros and then equal to. So the adiabatic algorithm, what it does is it starts with an HP, and then over time it evolves gradually from size at time 0 to size of t slowly, so that ultimately after a certain time t, it reaches the ground state of the problem Hamiltonian. Then you have your solution. But how do I go there? Okay. So I'll skip this. How slowly should we evolve? Okay? But basically, it is known that at each stage you have to choose the speed where the change in energy between two corresponding states is as small as possible. But it's very difficult to calculate that. And for combinatorially hard problems, NP hard problems, this would take many steps, almost exponential steps. So remember A to D conversion. So we have this analog problem. We ideal sampling would be at all these infinite number of points, but natural sampling would be at discrete points, and we then reconstruct that as much as possible. Okay. So what should be the we don't want too few, and we don't want too many. Okay. So analog to digital idea is also utilized here. So in a single iteration, you do two operations. Okay, UHP gamma and UHP beta. Okay, so with UHP gamma, the initial state goes here, and the UHB beta, it goes here. Okay, it's not a good solution. So that's one iteration. With another iteration, it gets a little better. And so ideally, with infinite number of iterations, you would get analog QA. But it is known that it's a sort of a discrete version of the quantum. So QAWA is a discrete version of the quantum adiabatic algorithm for optimization. So classically, you have to actually, so these betas and gammas are what is deciding the gradient at which it is converging. Okay, so you start with some kind of optimizer to get these initial parameters, and these are the quantum steps. You repeat these a few times, p times. Okay, then get the output. If it is not good enough, use the output to get some better beta and gamma, and then repeat again, okay, to get a good approximate solution. That's the idea of. So this is the first one that was designed was for the max cut problem. The problem is that you are given a graph, you want to partition the vertices into two disjoint sets as the number of edges crossing one set to the another is maximized. This is a hard problem. Computation takes exponential time. Not only that, finding classically a polynomial time approximation, which would have as close to optimal as possible, that is also hard. The best classical algorithm has this approximation ratio, and it's not possible to approximate better than this. Okay. So the quantum formulation goes like this. How much? Dr. Das?
Madam, we have time, no problem.
Yes, madam.
Please continue, madam. We have time, no problem.
Oh, okay. All right, thank you. So remember this was the problem, okay? So we associate with each vertex a qubit, and we are trying to find a partition of vertices. So the vertices which are in partition A, we start with some initial partition. The vertices which are in partition A, they get those qubits are in 0 state, and if you apply this, what is known as the Pauli Z operator, this is actually the NOT operator. So QZ of 0 state leaves it at 0, and QZ of 1 changes it by changes the phase. Okay. Sorry, QX is the NOT operator. QZ is this operator. Okay. And if it is in the B partition, then you have associated with state 1, and if you apply this, then this is what you're going to get. Okay? Now suppose you have an edge between U and V. Then the associated operator is written as a like this. That is half of 1 minus sigma z u and sigma z v. Notice, if U and V are both are in partition A, then the eigenvalues are both +1. Okay, so +1 times +1 will be 3 + 1. So Hamiltonian here is 0. Similarly, if both are in B, -1 gives +1, again this 0. But if one is in A and the other is in B, then one is +1, the other is -1, then this whole thing becomes 2, and half of that, so h of E will become 1. So we want to maximize overall edges, this sum of these h's, only then we will have the maximum value of h. So this is the idea which was given by Ed Farhi of MIT in 2014 to give a quantum approximate algorithm for max. So therefore you have Hadamard operation, and to get these so we had basically the Pauli Z operation, which is a rotation, first a C naught, a rotation, and then again a C naught, and then so this is the problem Hamiltonian, and this is the basis Hamiltonian. So this depends on the alpha, or what are known as the beta values. These are depending on the gamma values here. So in the first phase, it is gamma 1, and here it is beta 1. Then you repeat this with gamma 2. You repeat this sequentially with gamma 2, and then with beta 2, in this way, p times. Okay. So that's how you have a QAWA for max count. So if you have just a graph with a single edge, so this is the edge operator, okay, and for p equals 1, you will have this circuit, these operations. So the expectation value is a non-decreasing function of the depth of p. So if you let p to go to infinity, then you get optimal solution. If p is equal to 1, it was shown that for max cut, it's at least 0.692 for certain classes of graphs, which is better than random 0.5. Okay. The probability distribution generated by QAWA at p equals 1 cannot be efficiently sampled. So by random, In classical computer, you cannot get this. That is for sure. And the nice thing is that it has only 2 parameters. So the classical optimizer for deciding those gamma betas is you don't need too much time. But recently it was shown that you need, the number of iterations is not constant, but at least log of n, so that you can get something better than the classical and best known classical approximation for myself. And it turns out that actually, although this says that the expectation value is a non-decreasing function as a depth of p, ideally, but with noisy systems, Google showed that for p greater than 3, it decreases. Okay, the performance decreases because noise is the current. So we want to reduce noise, and to do that, we remember we had the quantum portion of the circuit. We want to make it smaller, and to make that smaller, we try to reduce the C0. This is some, and the reason we can remove that is because I won't go into this. Mathematically, you can show the effect of removing this C0, the first C0 before the RZ, will not give you any change in the partition. Okay, so there are certain conditions which C0s you can remove. Okay, so if you arbitrarily choose edges, you cannot guarantee many edges. So for each edge, you will have one C0 reduced if you can choose it correctly. So what we did was, in our recent work with IBM Research, we did edge coloring on the graph. So the colors are associated with the edges. So all the edges which are having the same color, they do not share any input. In other words, all the edges incident on the same vertex get distinct colors. So therefore, if two edges get same color, they don't have any vertex in common. So therefore, these qubits are independent. The 2 qubits for the 2 edges are independent, so you can have independent C0s. It's not that the target of one C0 is the control of another C0, so therefore it has to be sequential. Okay? So therefore, you can reduce at least half of the C0s. So this was the original circuit, and after reduction, you find that there are a number of reductions. Okay, so this was the original circuit. All these 3 C0s went away. Okay, because there were 3 color classes, you can do with 3 C0s, and this one is the HB part. This is the HP part. This is the HP. This was the problem Hamiltonian. This was the mixer Hamiltonian. Okay, and then again the next level problem Hamiltonian. The next iteration. It's only the first iteration that you can guarantee to reduce. Okay. So how many edges can you reduce? I'll skip through this. Basically, you can reduce at most, if there are n vertices, at most n multiple. Now we have another technique which is using depth first search. Okay, so the depth first search gives you of the graph. Let's assume it's a connected graph, and this was the original one. And then by this depth first search, what we can do is we can remove the first ones like this. Okay, so you find that all of these, the first C0 is gone. Okay, and you can actually reduce n-1, eliminate n-1 C0s. By edge coloring, you could remove n/2 here at most. Here you can remove n-1, but it comes at a price. So if we look at this, the edge coloring optimization of reducing the number of C0s, you could reduce 3 C0s for for a graph of 6 vertices, and the depth of the total number of cycles, which is the depth of the circuit, is 9. With depth first search, you can eliminate 5 of them, but the depth is slightly larger, okay? Because The rest of the edges you have to keep. But that's not too bad because, you know, if you take into account the amount of error, you will find that most of the um, systems, if the probability of no error comes to this, okay, the optimal probability of no error will happen if this particular, you can work this out. This is the probability of error for a control C naught gate. This is the probability of error because of the T1 is because of the relaxation, because the gate remains idle. Okay, if you take all that into account and do the mathematics, that means you can reduce K1 and the number of layers, that the depth increases for DFS by N1, but the C naught decrease by K1. And if you take this parameter, okay, as long as the number of the depth increases while is bounded by lambda times K1, you still get a advantage. Now this lambda depends on the technology itself, the probability of error of control C naught gate and the ideal. So existing, we tried with existing quantum IBM quantum hardware, and theoretically it should be greater than equal to 1, okay, and actually it is much greater than 1. So in order to get advantage of this reduction of C naught using depth first search optimization, you just need lambda to be greater than equal to 1, and this is assured by our current devices. So by this we used Qiskit and actually ran it on IBM Manhattan, and this is what I'd like to share with you, that for different graph families, you know, these graphs, these are the number of vertices. Complete graphs means you have all possible edges, that is 10 into 9 by 2, 45 edges if you have 10 vertices. So the traditional method needed 90 C naught gates, edge coloring gave 85. By DFS we could reduce 9, and as the size of the graph goes up, the reduction is much better. These are graphs with fewer, not that, these are, I mean the sparsity of the graphs are varied. Okay. So P is the not the number of iterations. This is the probability with which an edge exists or not. This is how we randomly generate graphs. So this is the sparser one, and here you find that you know, we get reduction in the number of C naughts, and the actual probability of error, if we look at that, the green one is what was originally there, blue is by edge coloring reduction, red is by depth first. This is for sparse graphs, and these for complete graphs. With dense graphs you get a lot more, and as your graph size increases, even then the probability of error does not degrade too far if you reduce the number of C naught. So let me conclude. I have run over 10 minutes. Error mitigation techniques are there to lower probability of error. I could not cover error correction, but some of them is by actual algorithm design, and the corresponding circuit design can lead to better algorithms. Okay. This one was for only the Maxwell problem. There are other combinatorial optimization problems which we are looking at. This holds for weighted graphs, and we found ways to tackle directed graphs also. What should we look ahead to? This is my final slide. So the probability distribution generated by Quava at p equals 1 cannot be sampled. So the parameter concentration, very few parameters, and ability to find these optimal parameters are hold promise for the Quavas. We would like to study this for other problems, and we hope that as time goes on, with better and better devices, technology of quantum devices, we'll have less noisy qubits, and we will be able to actually demonstrate quantum advantage. Thank you very much for your patience, and I'd be very happy to answer any questions if there is enough time.
Thank you, ma'am. Thank you for enlightening us with your valuable speech and sharing your knowledge with us. Now the session is open for question answer. If you have any questions, you can raise your hand or type in question answer chat box. Right now we have some questions in question answer chat box. The first question is, how many qubits of system is required to apply these quantum algorithms efficiently? Ma'am.
Yeah, just a minute. I'm trying to stop sharing.
Okay.
Yeah. Yes. Sorry. The question is, how many qubits of a system is required to apply these efficiently? Okay. What do you mean by efficiently? Right. So
Hello,
right
friends.
now, the what you have in particular, what you really have available is about, I think, 50 plus qubits. Okay. Now, in order the plan for IBM, the roadmap for IBM says that we are going to go to, in a couple of years, we are going to go to hundreds of qubits. Okay. Now, your question is to solve a quantum algorithm efficiently. For a particular quantum algorithm, the number of qubits, okay, it depends on what is the size of the input. It doesn't mean that the efficiency is going to increase if you increase the number of qubits. It depends on what is the size of your input, what is the size of the problem that you're going to solve. As I showed you, for the max cut problem, if you have a graph, if you want to solve max cut for 60 vertex graph, then you will need 60 qubits. Okay, to solve for, let's say, the factoring algorithm, if you are solving a problem, let's say your n is large, let's say it has 300 digits. Okay, so 300 digits would be that means 10 to the power 300. So you convert it into 2 to the power roughly 3000 or so. So you would need thousands of qubits to handle such things. Okay, if that answers your question. So the second question says, once more, the factorization problem of two big numbers using, if you can take number which is the product of two prime numbers and find the two prime numbers. No, the problem is that I know the two prime numbers. If I give you the product, you do not know the two prime numbers. How are you going to find the two prime numbers? Okay, that is the factorization. So in public key cryptography, what happens is there are two private keys. Two persons, they are going to communicate. I have my private key and you have your private key. These are the two big prime numbers. So, and there is a public key which is possibly the product of these two prime. I mean, there are many ways to do it. So possibly the product of these two prime numbers. So the product is known to everybody. Because I know one of the prime numbers, I can divide and get the other prime number. Because you know the other prime number, you can divide and get my prime number. But if somebody does not know any of the two prime numbers, it will take a long time to find out any one of the prime numbers. And without one of the prime numbers, you cannot decrypt. One of the prime numbers is used to encrypt, the other prime number is used to decrypt. So just by looking at the product of those two prime numbers, you cannot do unless you can factorize. Third
Okay,
question
thank
is,
you.
suppose I have
There is another question that is, how many qubits used be available in real quantum computer?
Yeah, so IBM over cloud allows 53 qubit. Google has announced, IBM is very soon going to announce 78 qubit, but it's still struggling with reducing the probability of error. Okay.
Okay, thank you, ma'am. And if anyone have any questions, you can directly contact with the madam. Madam, can you share your email ID so that participants can contact you if they have any queries? Okay, so you can
Okay.
directly contact with the madam
I
if
have
you have.